Okay, so we're going to start today with the dot product. Okay, so if you're given two vectors, three-dimensional vectors, so given vector A, and we're going to say A is going to equal A1, A2, A3, and another vector B, which is going to equal B1, B2, and B3. Well, A dot B will equal A1, B1 plus A2, B2 plus A3, B3. Okay? So let's just do an example of this first. Let's say we had the vector -1, 7, and 4, and we're going to dot this with 6, 2, and -1/2. Okay, so we're going to dot these two vectors together. Okay? So that's going to equal -1 times 6 plus 7 times 2 plus 4 times -1 divided by 2. Okay? So that's going to come out to -6 plus 14 and then -2. Okay? So what does that really come out to? That's going to be -6 and -2 comes out to be -8. And then -8 plus 14 is going to give us a +6. But vectors don't always have to be written this way. We have a special type of notation in this class involving i's, j's, and k's. So I equals 1, 0, 0. Okay, so that's just in the x direction. That's a semicolon, another j. J is going to equal 0, 1, 0, and k is going to equal 0, 0, and 1. So 0, 0, 1. Okay, so let's look at an IJK notation of doing the dot product. So let's say we had I plus 2 times j minus 3 times k, okay? And we're going to dot this with 2j minus k. Okay? So we're going to associate the i's, the j's, and the k's with each other. So we don't have an I in the first problem, the second one, okay? So that's going to equal 1 times 0 plus, now 2 times 2, and plus, I'm going to write it like this, say -3 times -1. Okay? So that's going to come out to 1 times 0 is just 0, 2 times 2 is going to be 4, and -3 times -1 is going to be just a +3, and so that's going to come out to be 7. Okay? But what does this really mean? We're saying we're doing the dot product, but what are the properties of the dot product that make it so nice? Okay? Well, let's say we're given two vectors in space. Okay? So let's call this vector A. Let's call this vector B. Okay? And the angle between the vectors we're going to call theta. Okay? Well, A dot B is going to equal the magnitude of A times the magnitude of B times cosine of theta. So the dot product is a way for us to actually calculate the angle between two vectors. Right? Now let's think about a property that would actually occur because of this. So we know that cosine of 0 is 1. And cosine of pi over 2 is 0. Cosine of 90 degrees is 0. So from this property right here, what do we get? If we have two vectors that are perpendicular to each other, okay, then A dot B would equal the magnitude of A times the magnitude of B times cosine of pi over 2, which would equal 0. So if A dot B equals 0, then A and B perpendicular. Okay? So, if you have two vectors that are perpendicular to each other, then their dot product is going to equal 0. So, why would this property be so useful? Well, one of the ways that, this is actually getting into another section, but this is an important property of the dot product, okay? So this is actually a major difference between the dot product and the cross product, is that if A dot B equals 0, the two vectors are going to be perpendicular to each other. Whenever we talk cross product, which I'll get to in a little while, if the cross product equals 0, they're actually going to be parallel to each other. In mathematics, this is the definition of what perpendicular or parallel is. Now, what's another really useful property of this being perpendicular? Well, it allows us a way to describe a plane. Okay? So, let's say we had a plane. Okay, so we're going to define a plane by the dot product. Okay, so So I'm going to call this point existing within the plane x naught, y naught, and z naught. Okay, so I've got a point in this plane that is going to be just a point in the plane. Now, any other vector that exists within this plane, okay, so let's say this vector or this vector, okay. And so I can call this one x, y, z. Okay. And so how would I describe these vectors? So let's say this one right here. Okay? This would be the vector okay? So it's always going to be the terminal point, which is xyz minus the initial point. All right? So, okay, so any vector xyz sticking out anywhere within this plane, any xyz point that exists within this plane corresponding to the initial point that we're dealing with right here would be described in this way. All right? Well, what can we say about every vector that actually exists within this plane? Well, what is it going to be? It's going to be perpendicular to a vector that is sticking out of this plane. Okay? We call this the normal vector. Okay? And so let's say n equals ABC. Okay. And since this vector is a, well, let's label it normal vector. All right. Now this normal vector is going to be perpendicular to every vector existing within this plane. Okay. Now, so from the last statement I said that if we do the dot product of two perpendicular vectors, that it's going to equal 0. Okay? So, what does this tell us? This tells us that if I dot product ABC with any vector that exists within this plane, it's going to equal 0. So, that means that A, B, C dotted with x minus x naught, y minus y naught, comma z minus z naught. Well, we know this is going to, oh, sorry, go off the screen. This is going to equal A x minus x naught plus B times y minus y naught plus C times z minus z naught. That's going to equal 0. Okay? So, what does this mean? This means that because of the dot product, this allows us to describe a plane. Because the normal vector that is perpendicular to the plane, its dot product with any vector that exists within this plane is going to be 0. So what is the equation of a plane? It's that right there. You have a point, x naught, y naught, z naught, that you know that exists within this plane. And then you have a vector that is perpendicular to all of those vectors within that plane. And by setting it equal to 0, we actually get the equation of a plane. So this is one of the useful properties of the dot product, is that, yeah, it'll actually tell you, it'll give you the equation on how to describe a plane. Okay? We have just a couple of useful more facts about the dot product. And I'll go on to the cross product. During the next class period, we'll do a lot of examples. I'm just trying to get some of these definitions out of the way. Okay? So, what are some other useful properties of the dot product? Okay? Well, let's say we were trying to calculate the magnitude of A. Well, the magnitude of a vector is actually just equal to the square root of v dot b. So it allows you to actually calculate the magnitude of a vector. Okay? And this is in the normal Euclidean sense what does it end up boiling down to? It boils down to Pythagorean theorem. So if you have V, which equals, let's say, V1, V2, and V3, well, what's the magnitude of V? It's going to be the square root of V1 squared plus V2 squared plus V3 squared. Okay? So the dot product itself allows us to find a way to calculate the magnitude of the vector. All right, we have another nice little property of the dot product. This is called, well, instead of the magnitude vector, why don't we try to project a vector onto another vector? So, let's say we were going to try to project the projection of a vector, let's say B, in vector A. Okay? So this would be the projection of B onto A. All right, so this would be B dot A divided by A dot A and then multiplied by A. So the dot product also allows us to do projections. So let's do a simple one. So let's say we'll do that. We'll just do this in 2 dimensions. Three. 1, 2, 3, and 4. Say A is going to equal 3 and 4. Let's say B equals 1, 2, 3, and up by 1. So I'm using slightly different notation. See, vectors can be written as column vectors, or you can write them as right to left. I'm trying to save some space by writing them like this. So let's say we did the projection of A onto B. Yeah, let's do the projection of A onto B. Well, okay. Okay, so now whenever you do this, whatever you're projecting onto, all right, so in this one right here, we're projecting onto A, so there's a whole bunch of A's in the problem. Now this problem right here, we're projecting A onto B, so there's going to be a whole bunch of B's in the problem. So this would be A dot B divided by B dot B, and then multiplied by B. Okay? So, okay, so I can rewrite this as, where's my A at? That's going to be 3, that's going to be 4. Let's go to dot it. -3 or 1. Now divided by -3 and a 1, dotted with -3 and 1, and then multiplied by -3 and 1. Okay. All So that would come out to 3 and negative 3. That would be negative 9 and then plus 4 divided by negative 9 and 1, and then multiplied by negative 3 and 1. Okay? So that would equal, all right, it's negative 9 plus 4 is negative 5. That would be 10. And that would be negative 3 and 1. And I'm kind of running out of room right here. So we'll just continue it onto this page right here. Okay. So that would equal, okay, so negative 5 over 10 is negative 1/2. Okay? So negative 1/2 times negative 3 would be positive. And that would be negative 1 over 2. Okay, so 3 over 2, negative 1 over 2. What did this thing just do? If I look at my picture right here. So positive 3 over 2 and negative 1 over 2. That guy would appear right there. And what does it do? It actually flipped that around and it projected this vector onto a vector that was parallel to that vector right here. So this vector right here is the projection of A onto B. And it forms a perpendicular line with it. This is not the useful aspect of the dot product. It allows projections. In this class, we're going to deal with, this is kind of a simple problem that I wouldn't actually put on a test, this projection. When you get into other classes, like if y'all have taken linear algebra, you understand that you can actually project vectors onto planes. And it seems to fit with this class, but it's more of a linear algebra problem, so we won't be going over that problem.